One thing you can do with matrices is you can encode and decode messages. For instance, if you, this is called cryptography, and so if you had a company that was sending emails, or if you wanted to make sure credit card numbers were secure, or if you were a military service and you didn't want people to get your information, you would have to use some sort of cryptography to secure your communications. So this is just a simple technique. Don't try this and think that you can get away with anything, but it's a simple technique. All you need is a matrix and its inverse to encode and decode messages. So let me show you what we're going to do. I'm going to just take a simple message called secret code right here, and I'm going to just look at the alphabet, and you can write out the alphabet if you need to, but S is the 19th letter of the alphabet, E is the 5th letter, C is the 3rd letter, R is the 18th letter, E is the 5th letter, and T is the 20th letter. Now, I have a space here separating these. You can do this with or without spaces, but let's say for a space we're going to use the number 0. So that'll represent a space. And then for code, I have C is the 3rd letter, O is the 15th letter, D is the 4th letter, and E is the 5th letter. Now, how I write this in matrix form depends on what I'm going to use to encode it. If I'm going to use a 2x2 matrix to encode the message, which that's what I'm going to use this time, I'm just going to use this matrix to encode the message, then this message matrix must be written as a 2x something. I don't know what yet, but it must be written as a 2x something. So the way to write this message, these numbers, as a 2x matrix is simply to take the first two numbers and make them be the first column. So here's my message matrix, and so the numbers 19 and 5 will be the first column, and that way I'll have 2 rows. So, and then the next two numbers, 3 and 18, will be the next column, and then 520 would be the next column, 03 would then be the next column, 15.4 would be the next column, and then notice I don't have a number to finish this out with. I just have the 5 left. So let's just pretend like there's another space out beside that 5, and we'll put a 0 there, and then that way I can write 50 as the last column. Okay, so that's my message matrix. Now again, the reason I need it in this form is this is now a 2x, looks like 2x6, and in order to encode this matrix, what I've got to do is I've got to multiply this matrix by my encoding matrix. And notice that the encoding matrix here is a 2x2. So remember, I can only multiply a 2x2 matrix by a matrix that has 2 rows, because remember, these inside numbers must match. So that's why I had to have this message matrix be a 2-row matrix. Now I'll let you do the arithmetic here, but you can multiply this together on your calculator if you want to. Actually, you can do a lot of operations on your calculator, but if you multiply this row with this column, you'll get 76 plus 15, which is 91. And then this row with this column will give you 12 plus 54, which is 66. And then this row with this column give you 20 plus 60, which is 80, and so forth. So you can just check the arithmetic there. But this is the new matrix that I get. Now, I'm going to take this matrix out just like I put it in, except in reverse order. Remember, I put it in column by column, so I'm going to take it out column by column. So 9124 is my first 2 values, then 6621 is my next 2, and then 80, 25 is my next two, and then I have 9, 3, 72, 19, and 25. So this would be the message that I would send if I wanted to send this to someone so that it couldn't be read by anyone else. This is the message that I would send to someone else. Okay, so when I send it to this other person has to know how to decode this message. But here's the catch. All we have to know is that this is our encoding matrix. That's all we have to know. Because to decode the message, all we need is the inverse of this. And as long as I have this matrix, I know how to find the inverse. Alright, now we're not going to do that here. I'm just going to go ahead and tell you that I found that the inverse of this, I found it to be this matrix. Now, guys, generally if you were going to do this, you would have the inverse determined beforehand anyway. But honestly, if you know how to find the inverse of a matrix, all you have to memorize is this matrix, and then you can use an algorithm or computer or do it by hand to find the inverse like I showed you before. But let's take a look at what's going to happen. To get back my original matrix, message matrix M, I'm just going to take the inverse of A and I'm going to multiply it by AM. Now think about this mathematically, what that does. That's A inverse times A. Well, guess what A inverse times A is? That's the identity matrix, right? And then if you read the section, you saw that the identity matrix times M, anytime you multiply the identity matrix times the matrix, it just gives you back the matrix M. So basically, multiplying A inverse times this matrix that I called AM up there, this matrix here is AM. So if I multiply the inverse times that matrix, it's going to unscramble the message. And you can check this yourself, but if I multiply this row by this column, it should give me 19. And then if I multiply this row by this column, it should give me 3. And if I multiply this row by this column, it's going to give me 5. And then this row by, where am I at now? This column is going to give me 0. And then this row by this column is going to give me 15. And then this row multiplied by this column is going to give me 5. You can check it yourself. And then if I take the bottom row and multiply it by each column, it's going to give me the 5, the 18, the 20, the 3, the 4, and the 0. So whoever the person is on the other end, after they've multiplied these matrices together, can now take this out and the way that we put it in: 19, 5, 3, 18, 5, 20, 0, 3, 15, 4, 5, 0. And guess what? Now they have the message SECRET blank CODE, secret code. And there you go. And so that's one application of inverses of matrices. You can also do this with a 3x3 matrix. So here I just showed you. I'm not going to spend a lot of time on this, but if you wanted to use a 3x3, you would want your message matrix would have to be in a 3x. So notice I put 19, 5, 3 is the first row, 18, 5, 20 is the second column, 18, 5, 20 is the second column, 0, 3, 15 is the third column, and then 4, 5, and then I had to fill in with a 0 for the last column. And so all I have to do now is get a matrix that I know the inverse of, like this, and then I can multiply this matrix times this message matrix, and now I have encoded my secret message using a 3x3 matrix. Pretty cool, huh? So you can read the rest of the notes there about encryption, but also make sure you read properties of matrices, and you'll see several properties here that are really similar to real numbers, but one thing I do want to mention is that, first of all, matrix multiplication is not commutative. Remember, there's no commutative property. And so when you do this left distributive property, a times b plus c, it equals ab plus ac, but b plus c times a equals ba plus ca, and that these two are not equal because matrix multiplication is not commutative. Okay, real quick, I want to show you solving a matrix equation. There's two here, but I'm just going to do this one because this is the one that's important for my next example. To solve this matrix equation, I'm going to multiply both sides. I want to solve for x, so I'm just going to multiply both sides by A inverse. See, there's no division operation with matrices. You have to multiply by the inverse. Then when I multiply A inverse times A over here, well, A inverse times A is the identity, and the identity matrix times x is just x. And on the right hand side, I just bring it down. So x is equal to A inverse times B. Now, how does that help me? Well, let me show you how to solve a system of equations using the matrix inverse method. Okay, so let's say we want to solve this system of equations. Alright, let's say the coefficients are the matrix A. So the coefficients are 1, negative 3, 7, negative 1, 4, negative 7, negative 1, 3, negative 6. So here's the matrix A right here. This is matrix A. Okay, I'll get that out of the way now. Okay, so let's say the matrix that represents my three variables is matrix X. So this is the matrix X. Okay, now, so I have an equation here, AX equals, and these are my coefficients. This is B. So I've got the equation AX equal B, right? Well, I just found up here that if you want to solve the equation AX equal B, all you have to do to solve for x is find the inverse of A and multiply it by B. So if I can find the inverse of this matrix and then multiply that by this matrix B, then I can get the answer. So we found the inverse of this matrix in an earlier section, and here's the inverse of it. Okay, so here's the inverse of A. Here's B. If I multiply those two matrices together, notice I did that over here. If I multiply these two matrices together, it gives me an answer, negative 19, 0, and 3. You can do the multiplication yourself. So the solution is negative 19, 0, and 3. Now that may not seem like a great feat, but let's say that you had several of these systems of equations, but the only thing that changed was these constants. So for instance, here we have 2, negative 2, 1. Down here I have the same system, but the constants are 3, 1, negative 2. Over here I have the same system, but the constants are 1, 5, and positive 2. Well, since the coefficients are all the same, then I could solve them the same way using the inverse of the coefficient matrix. So just like I multiplied this matrix by the constants here, I could multiply this matrix by this set of constants to get the answers. I didn't do it. You can do it if you want to. And then I can take this inverse matrix again and multiply it by this set of constants to get the answers. So the point is, if I had several of these systems to solve where nothing changed but the constants, then once I found that inverse matrix, I can solve any system as long as I have the constants. Now, your calculator, when it solves systems of equations, it uses an algorithm similar to this to actually solve systems of equations. So anyway, that's pretty much all I have to talk about on this. There's one more section I want to get into, which may or may not be covered in your finite math course, but I'm going to cover it just in case.